Hello, everyone. Welcome. Thank you for our online diagnostic training session. If you have any questions, if you're on Zoom, please put it in the Q&A box. So if you look at the top or the bottom of your screen, you can see Zoom controls up on the top or bottom. It should look like two chat bubbles next to each other. It should say Q&A. Click on that. It'll open a new window. You can then type in your question, and I'll get to them at the end. If you're watching this on YouTube, make sure that you can utilize the chat function. So you can type in your question there. I know we have a few people monitoring. We'll be able to either answer your question or I can answer it live at the end of the session. So my name is Jason Gabrenas. I am one of Snap-on's national diagnostic trainers. Been in the training department the last 7 years, and I've been traveling around North America helping technicians and shop owners get the most out of their diagnostic equipment. Before I did that, it was 2 years as a diagnostic sales rep with Snap-on. So I had 30 different Snap-on franchisees that I worked with and helping them as well as the shops that they service get the most out of their diagnostic needs. Before that, it was 8 years at Subaru. So I was a technician at a Subaru dealership, and I seemed to end up becoming the default diagnostic person in the shop, right? So I always ended up with those drivability problems, those intermittent problems, the weird wiring problems that would come across. So that's really where I cut my diagnostic teeth, was trying to figure out all those real head scratcher problems that we had with those cars. Before that, a bunch of other miscellaneous wrenching jobs. It's been about 25 years under the hood for me. So our topic is ADAS level, what we're calling ADAS level 2. And this will be focusing more on the actual components of ADAS and the component testing. If you were with us in our previous session, we covered a very high level overview of ADAS, just how it operates and how it's set up and how we might reset and relearn those systems. Today, we're going to talk more about our actual diagnosis process. So if we think about our diagnostic workflow, always good to have a nice repeatable diagnostic workflow, especially when you're working with complex systems such as ADAS. So first off, we want to make sure we do a pre-scan with our scan tool, right? So we want to go in, we want to scan all modules for codes because, especially with some ADAS systems, they may store a code but not turn on any sort of an indicator lamp. So if we don't have an indicator lamp, we might assume that there aren't any codes in there, but we always want to double check. So do that one-touch full vehicle code scan, pre-scan the vehicle, check for codes in all systems. And then once we've done that, that gives us a starting point. And then it would be time for diagnosis, right? We want to determine the actual cause of the problem. Now, it could be fairly simple. It could be the vehicle's been in a collision and the sensor's in 100 pieces on the ground. Pretty obvious what might need to be done there, but there could also be a wiring issue. There could also be an internal wiring or electrical issue inside the module as well, if it's not so visually obvious. Then once we've determined what the actual cause is, then we'll move on to repair, right? Fix the problem. We replace the sensor, replace the module, etc. Maybe we replace or repair the wiring harness. Then we need to recalibrate. More often than not, especially if it's ADAS, we need to perform some sort of recalibration. So either our static, dynamic, or reinitialization there and reset the system. Then after that's all done, once the repair is complete, the calibration is complete, we want to take it on a road test and then do that post scan. We want to verify that there are no codes left over in the vehicle and it's back to as good as new can be. All right. So as far as this course, what we're going to cover, it's going to stick mainly to that diagnostic section of the workflow. So we'll talk about our 4 main sensors in ADAS. This is where we're going to spend the bulk of our time today. So we'll talk about radar, ultrasonic, camera, and Lidar sensors. So radar uses electromagnetic waves, and it bounces those electromagnetic waves off of other objects around. It could be short range and long range. So generally the long range will be for maybe your adaptive cruise control where you have to see other vehicles. And then short range would be oftentimes for maybe cross traffic alert, automatic reverse braking, that sort of thing. Also can judge other cars' speed and distance in real time, like I said, often used for speed control, cruise control. It is a relatively high cost compared to some other things on a car just because of the technology involved, and to miniaturize it costs a decent amount. It also gives us robustness to rain, snow, and fog interference. So those beams can just cut right through rain, snow, fog, etc. Then we get to ultrasonic. So ultrasonic emits ultra high frequency waves that bounce off objects. Generally a short range, about 2 meters or 6 feet. It's applied in very low speeds. Usually the only time we see these on a vehicle is for object detection, maybe backup or forward object detection as well. They are relatively inexpensive. They're a pretty simple sensor in design, and snow and rain can interfere with these. So if you think about heavy rain, heavy snow, the sound waves can bounce right off and maybe misdirect where that beam is bouncing. Then we get to the camera. The camera is pretty popular. I mean, I think most vehicles nowadays have at least one camera on them. It's usually the one up on the top of the windshield there. Often used for color and font identification. There's also generally short and long range versions of a camera if you think about it on a car. Because usually the long range will be that one up on the windshield that's pointing out the road. Often, let's say, the 360 view system. So that'll be a very wide angle lens, but you can't really see very far away from the car, but it'll be a very long or wide distance. Often used for traffic signs, lights, lane marker identification. Does require significant computing power. So if you think about a video signal, it's very complex. So it does require often a lot of computing power in order to make the signal transmit. And then weather conditions can interfere. So if you think about a camera is not much better than your eye, right? So you have, if you can't see through the fog or the snow or the rain, well, then the camera's probably not going to be able to see much further than that either. And then we get to LiDAR. Now they've had LiDAR on vehicles off and on here and there throughout the last 10, 20 years or so. Really hasn't hit mass market up until the last couple of years. So that uses a laser beam. So it's emitting light, right? Short and long range once again. So short range for object detection, long range for other vehicle detection, often used in conjunction with the radar. And it is more expensive than radar. Now the cost is going down, but we already said that radar has a relatively high cost. So this is even more expensive than that. Also, the other advantage LiDAR gives us over radar is there's no interference or metallic material reflection. Radar has a hard time dealing with metallic surface because that's really what it's designed for, is to bounce off metallic surfaces. And LiDAR really doesn't have that problem because it's using light instead of radio waves. So let's talk about radar a little bit more in depth. So radar stands for radio detection and ranging. And as I said before, it works by transmitting radio waves, and then it calculates how long it takes for those waves to return back to the vehicle. So radar, as well as the ultrasonic and as well as the LiDAR systems, all operate on this thing we call the Doppler effect. So the Doppler effect takes into account the radar is transmitting at a set frequency. The vehicle or the computers know what frequency that is, and it just sets it out at a single locked frequency. When that beam bounces off an object that is approaching us, or maybe we're approaching it, like maybe there's a slower car in front of us and we're approaching it at a higher rate of speed, the reflection will begin to stack up and it will give us a higher frequency in that reflection. Other side of that is if the object we are approaching is going away from us, maybe they're traveling at a higher rate of speed. So the reflection takes longer to get back. So the reflection is a lower frequency. So judging by where the frequency is the frequency higher than what I transmitted or frequency lower than I transmitted, the radar can decide, is it going away or is it coming back? If you think about it, you also may have dealt with this before, maybe a motorcycle going by or a fire truck with a loud siren going by. You know, the pitch of the siren or the motorcycle gets much higher as it gets closer to you. And then as it travels away, since those waveforms are getting further apart, then the frequency goes down and the sound gets lower in pitch. All right, so it's the same exact principle. It's called the Doppler effect. So that's really what we're dealing with when we're dealing with these systems. That's how they work. So common applications for radar. So most common probably would be adaptive cruise control, right? That's been around for a fair amount of time. And that's where you can use that radar to lock onto the vehicle in front of you, so to speak. And then it keeps the distance, judging by that Doppler effect, right? So if the frequency gets a little higher, we slow down, gets a little lower, we speed up, and it keeps you that same distance away. Also often used for cross traffic alert. So that'll be your shorter range radar, usually in a bumper. And that way you can be sure that traffic isn't crossing in front if you're trying to pull out of a parking spot, say. Blind spot detection, once again. So that's radar usually in the rear, and that will be looking for objects in your blind spot. If you can't necessarily see to turn around or what have you, it'll give you an alert when there's something in your blind spot. And then rear collision warning. right? So you're backing up, you can't see something behind you, and maybe it gives you a warning. Maybe it even puts on the brakes for you. I remember seeing a commercial not that long ago. It's a gentleman backing down his driveway, and he doesn't see the trash barrel behind him, and taps on the brakes for him so he doesn't run over his trash barrel, right? So that's a nice convenient feature, and that's using radar. So let's look at a real world scenario where we might see radar and say a blind spot radar system on a 2017 Land Rover Discovery Sport. All right, so I'm going to look up the information using Shopkey. So Shopkey and Mitchell both have this button on the quick links bar right on the home page, specifically for ADAS functions. So if I go into my driver assist, ADAS functions, it gives me this table. Now in this table, we have a list of components, list of jobs on that component that possibly require calibrating, if we need special tools such as targets, and then if we need a scan tool to do it. So we go down here to the blind spot sensor. We see to replace the blind spot sensor, we may need a scan tool. Perfect. So we click on blind spot sensor. That's a link. And what it'll do for us is it'll add it as a search term in this box up here. And this is our search result page. We see we have, it says 8 different category cards. We call these cards. And they have different categories of information filtered out by whatever's in the search box. So in this case, these 8 topics, everything in behind these 8 topics, if we're to click on them, relates to the blind spot sensor. So we'll go into component location first. Where is the sensor, or where are the parts of this system on the vehicle? So we go into component location. It brings up a little diagram from the manufacturer. We'll go and view full screen, make it a little bigger. And we see we have the 2 radar modules on both sides, in the rear of the bumper. Also the rear cameras in this picture. We also have the mirrors. Now, why are the mirrors in there? Because they have LEDs that alert you if there is someone in your blind spot. Front camera, also other miscellaneous modules, control modules in the doors and underneath the dash up there as well. So this is showing multiple features and functions of different systems. So now we know the sensors are in the back. How do they operate? So we go to component operation. So we take a look. This is a little diagram. There would be your Land Rover, and there would be the blind spot. These boxes right here would be our blind spot on the vehicle. So it'll be transmitting a radio wave through the radar. If it doesn't bounce off of anything in this distance, then there's nothing in your blind spot. Say this side, bouncing off of this vehicle, which is inside your blind spot area, it'll return a signal and it will light up in your mirror and say, hey, there's a car over there. Don't change lanes right now because there's a vehicle in your blind spot. So it gives you a little warning on a little warning light in there. Now, if we want to know other ways that it operates, like how does it communicate with the rest of the vehicle, here's a little topographical overview. So we have the controller there, and then we have the vehicle's main network. It's a 2-wire CAN bus network. Goes to the gateway module. Now, many vehicles have gateway modules. Just think of it like the router on your car. So like a router at home would be the router on your car. It routes the signals where they need to go. We'll see on a different network, we have the door modules. So you see it's a different color there. So we have different modules there. Then we see back on the main vehicle network, it goes to the 2 blind spot monitoring control modules. That's what that is. Both connected to the main vehicle network and also have their own network, 2-wire network in between the 2 modules there. If we wanted to look at an actual wiring diagram for this, we can pull that up. We see the left module here, the right module there. On pin 8, they both share power input. On pin 3, on the left-hand side, we get power. On the right-hand side, we get ground. That's how they can differentiate what side of the vehicle that module is on. Does it have ground at pin 3 or does it have power at pin 3? Then pins 1 and 2, that is our network between the 2. And then for the high-speed CAN out to the vehicle, that's pin 6 and 7. And then pin 5 is ground on either side. So we're looking at power, we're looking at ground, and we're looking at network communication. So we'll talk more about testing a little bit later when we go live on the tool, and we'll go through some actual tests on all of these different systems. Next, we get to ultrasonic. So ultrasonic sensors, as I said, works by transmitting super high frequency audio waves and calculates their return time. Generally, the only place we find this on a vehicle is going to be for park assistance. It's a very short range. I don't know if there's really any other applications they'd be used for. And they actually been around for quite a while. I remember doing those aftermarket, in the shop there. So often park assist, as I said. So let's look at this 2014 Cadillac ATS and talk about the park assist system on this vehicle. All right, so here's a little component operation. I'm going to come down here on the bottom. So when an object is within the measuring range of the sensor, the ultrasonic pulse is reflected and is received by the sending or a neighboring sensor. The sensor converts this signal into a voltage signal and sends this signal to the parking assist control module. The park assist control module then evaluates the received signals. As soon as an object is within the measuring range, the park assist control module sends a message via serial data to either the radio or the seat module to provide an alert signal. So the radar, you would hear an audible tone, and then the seat module would vibrate the seat depending on how the vehicle is equipped. So it says the parking assist system can detect objects greater than 3 inches wide and 10 inches tall. It cannot detect objects below the bumper underneath the vehicle. If an object is detected, one of the following will occur. So if it's between 1 foot and 4 feet from the vehicle, the acoustic signal will become active, so you'll hear an alert tone inside the vehicle. The frequency of that beep sound will increase with decreasing distance. So the closer it gets to the object, the faster a beep. Once it gets within a foot, you'll hear a continuous tone. So it'll beep, 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 be a constant tone once it gets within a foot. And then also if it has a vibration function in the seat would vibrate accordingly as well. So that's a little background on how it works and how it helps us when it comes to parking. Here's a remove and replace a line drawing of where that sensor would go. So it looks like a front bumper, and we have the bracket here. It's a little plastic bracket, and it has some clips, and it would clip in here, and we have the wiring goes in over here. We pull up a wiring diagram. You see, as we said earlier, is a fairly simple system. Right, so we have the front bumper and the rear bumper. They're grouped together. Front bumper will share common ground and common power amongst them. They also have signal wires individually that go back to the module. So the module knows which sensor is receiving which signal. So they have an individual signal wire, common power, common ground. So that's what we're measuring if we're going to be testing these components, be power and ground and signal. Now let's look at the camera. So camera, here's just a basic picture of a camera module, one you'd probably find up in the rearview mirror area, top of the windshield. So camera works very much like an eyeball works. So it has a lens and it converts light into electronic signals, which is actually what your eyeball does too, right? So the light comes in here, there's the lens, comes in, and we see this green board right there. And attached to that green board, we have this gray chip. This gray chip is the light sensor. So when light hits this sensor, depending on colors, etc., it will create an electric signal, which is then transmitted to the processor, which then sends it out to the vehicle to be interpreted however it's programmed to do that. Common uses for the camera is going to be a lane departure warning system, so it sees the lanes markers. Traffic sign recognition, so it can recognize stop signs, speed limit signs. You may have seen that on a vehicle before. I know I have. Using cruise control, it puts a little speed limit sign on your screen sometimes. Surround view system, so those would be your shorter range cameras, and that allows you to see all the way around the vehicle when you're trying to park. And then parking assist, a rear view camera mounted in the bumper, so we can see when we're backing up, or we could use the 360 camera as well. So let's take a look at a 360 or surround view camera system on this 2016 BMW. First off, component location. Where are the components located in here? So it sees we have one on each side of the front bumper, one in each mirror, and then one in the rear. Now, as far as our range here, I think the rear would probably be about 180-degree sweep, so you'll be able to see the entire background of the vehicle. And then the side mirrors, I would imagine, be pretty much the same. So those would come out like this, and you'd have about 180-degree or so there on both sides. And then in the front, you would have overlapping coverage with the mirror, I would imagine, and then comes around somewhere in the middle here. They all transmit into the module, the video processing module. The video processing module then stitches all of those pictures together and gives us our 360-degree view around the vehicle. If we want a little closer view of that mirror, we have the camera here on the bottom. We have an LED for the turn signal, and then we have the plastic piece for the color, trim color. Now let's imagine if for some reason the LED turn signal burned out for whatever reason, and we needed to replace the mirror because it's not replaceable. Then we would have to calibrate that camera. Even if we didn't replace it for the camera, it was removed and replaced. So now we have to calibrate that camera. All right, so that brings us to our scan tool where we calibrate that. If we want to look at a block diagram of this, there's our front cameras there on the top, and then we have our mirror cameras there, and then we have our rear camera here. And you'll notice each camera has their own bundle of wire or its own individual cable going from the camera to the video processing module. The video processing module is also connected to the head unit and the information display. So it would display the video on there. You see there's also FlexRay and CAN bus also involved in here. So we go to the actual wiring diagram. We see, once again, they're bundles of wire. There are four wire connectors, and there's a fifth. They call it not really a connector. So it's a fifth. We'll say it's a connector, but it's not really a connector on the plug because it's actually the shield. It's a shielded bundle of wire to keep out radio frequency interference. So it has a braid around it, which you do not want to break. And now we'll get to Lidar before we get to testing. So Lidar is very similar to radar, as in it uses light. So we use radar is radio detection and ranging. Lidar is light detection and ranging, as it uses a laser beam in order to detect objects. So it transmits the light waves and calculates the return time using that Doppler effect we talked about. So we have this is just a little cutaway view here. So we have a laser diode, generates a laser beam, emits a laser beam, bounces off this spinning mirror. The spinning mirror spins at 750 RPM, and then it sends that beam out. It looks like about 145-degree beam width, right? So not quite flat, 145 degrees. If it bounces off something, it'll come back and return to this receiver unit, which then translates that to an electric signal, goes to the processor, goes out to the vehicle, and then the vehicle can use that data however it's programmed to do that. Really, over the years, it's been the automakers have been dabbling with this. Until really recently, there weren't many mass market cars that had this on here. It was a 2018 Audi A8 was the more recent vehicle that first started using this. So common applications with that would be adaptive cruise control, using in addition to the radar most often. Also good for pedestrian detection, because we can really, this is what they use this technology for 3D mapping. So it's able to detect objects pretty much anywhere in its field of view. And then emergency braking. If it does detect an object, it can be used for emergency stop of the vehicle. So let's look at a 2019 Audi A8 and the Lidar system and how this is set up. All right, so this is just straight from Audi. We don't have a ton of information on this system, but what we do have, we'll share with you. So this is just straight from Audi, right from their website. And we see the different sensor arrays around this vehicle. So we have the camera there. Radar is all the green triangles here. So we have radar out the front. The red is the laser. So the laser is used in conjunction with the radar, in conjunction with the camera, in order for that distance control. It's really used for cruise control at this time, and also some emergency braking. There's just another view of that cutaway. Another interesting thing on this that I noticed, I live in a cold climate, right? So I also noticed they put a heated front screen on there. So it's like a defroster grid almost on this glass cover here. So I thought that was a pretty good engineering little add-on there, right? So the laser won't work if I have frost or ice on the glass. So I thought that was pretty interesting. If we pull up the wiring diagram there, we see here's the laser module down there. They call it a laser distance regulation control module. And then we have the adaptive cruise control module, which runs the whole adaptive cruise control system. They both share common power. That's this black and red wire. They both have output 2 wires to the computer data line system, which would be out to the vehicle's CAN network. And then they also have a 2-wire CAN in between them. And then they also have found on pin 1 as well. So in this one, we're dealing with power, ground, and network signals. Here's just another close look at the connector there. We have pin 1, which would be our ground, and then pin 8 would be our power, and then 6 and 7 there, and 2 and 3 for our networks, and then 4 and 5 are blank. Right, so, or 4 and 7 would be blank. So we see that there's our example there. So with all that little background, let's now switch live to the tool. So let me go here. For those of you just joining us, if you're on Zoom, Please make sure if you have any questions throughout what we've covered already or what we're going to cover soon, just make sure you put it in the Q&A box. It should be on the top or the bottom of your screen, little button says Q&A. If you're on YouTube, I see there's a few people in chat there, so keep those questions coming if you will, and I'll make sure I address them as we can at the end of the presentation. All right, so here we have our tool, and the easiest way we're going to be able to test these electrically is we're going to want to use our guided component test because it does a lot of the work for us, and there's a nice database of all the information in there. So it is VIN-specific information. I need to ID a vehicle. We're going to go through 3 of those sensors. So we'll go into vehicle history, and first one I want to pull up is my Cadillac ATS with the ultrasonic sensor. So I'll activate that vehicle. See, I have my vehicle in there now. And then I'll go into guided component test. Once we load in the guided component test with a vehicle, we could either ID a vehicle from scratch or we could pull it from history as I did here. We see the different systems that we can test components in. So in this case, we have, let's see, 4, 8, 9 different systems that we can test. We have up to 12 systems depending on how the vehicle is configured and what information we have. Goes all the way back to 1981, this information, and covers 28 different brands of vehicles. So there's a wealth of information in here, over 5 million individual guided component tests in here. So in this case, I want to test ADAS equipment. So we'll go into driver aids and ADAS. Now for this car, we have the front view camera, object detection sensor, or the park assist. We talked about park assist in the material. So let's go there. All right. And then we have the park assist module, park assist sensor, and the rear view camera. So we talked about the sensor. So let's go in there. And we'll go into component information. Once we have a component selected, every component has component information listed so we can understand a little bit more about how it works. So we'll go into component information, tells us how it works. So it's designed to identify and notify the driver of an object in the vehicle's path when reversing at speeds of less than 5 miles an hour. All right. And then down here, it tells us our location. So where is it? So the sensors are mounted in the front and rear bumpers. And the best test location, because it's not always in the same place, maybe it's hidden somewhere on the vehicle. In this case, the test location is at the park assist sensor, is the best place to go. We also have connectors and pin assignments over here. So you can see a connector. Here's, for example, the front left outside sensor and what each pin does on there and the corresponding wire color. So all this information before we even start a test. And this is stuff you would have to find in many different locations if you didn't use this, right? So we have a few tests we can do. We could have between 1 and 6 tests that we can do for a sensor or perform. In this case, we want to perform a DC voltage test. So go in here. Once we're in a test, it's going to tell us where to plug in our color-coded test leads. So the top of the tool is color-coded, and channel 1 is yellow. So yellow goes to object sense voltage control circuit. So in this case, that would be pin 1. And then black goes to a known good ground. Now, a known good ground, that is key. We want to make sure we go to an actual known good ground. We don't want to guess that the ground for the sensor is correct because that could be our problem. We could have a bad ground on a sensor. So ideally, you'd want to go back to maybe an engine ground, body ground, or the battery, right? The easiest place to get to a known good, I know this ground is good. And then it says, put the vehicle in reverse with parking brake applied. And then the front sensors, if it has front sensors, those will activate in reverse as well, or when placed in drive up to 5 miles an hour. Each of the parking assist sensors should have 8 to 9 volts applied from the park assist module. So this is not battery power. It's not 5 volts. It's between 8 and 9 volts, and that comes from the module. So if I suspect I have a problem on one of these, I would test for voltage, right? So we have view meter. In guided component test, it automatically sets the voltage range where it needs to be and automatically sets the time base where it needs to be. So I don't need to go in and manually set any of this up. So we see we're looking at, looks like a graphing meter here and a little over 8 volts, somewhere between 8 and 9 volts on the screen. All right. So in this example, that would be a good picture, right? We want to see between 8 and 9 volts. We saw 12 volts or 14 volts. That'd be a short to battery power or alternator power. I should suspect a short there. If we saw 5 volts, more than likely it's a short to 5 volts, but it could be a resistance problem that happened to bring it down to 5 volts. I suppose there could be occasions where that happens, but more often than not, more likely than not, it would probably be shorted to 5 volts there. If we had 0 volts, then we most likely have an open in the circuit there, and we'd have to investigate that. All right, so we see that's how we would test the power. Okay, so that is the ultrasonic sensor. Now let's go look at camera. So we'll go to the BMW, load that in there, go to Guided Component Tests, confirm our vehicle, go to ADAS. And here's all of the modules or all the sensors on this ADAS for this BMW. So let's go to the left mirror camera, because that's where that's what we were talking about in the material there, right? So left mirror camera, component information. So it uses the all-around vision cameras, use the rear view mirror camera along with the bumper and reversing camera to give a 360-degree view of the vehicle as part of the peripheral monitoring system. The camera sends their signals to the LVDS data line, and then the head unit transmits the image data to the information display, so we can see a picture on the screen. Location of it, the left side mirror camera is located in the left mirror. The camera control unit is located in the passenger side footwell and the A-pillar. Best test location is at the camera control unit connector or at the driver's side mirror camera connector, depending on what's easiest to get to. In this case, for testing multiple cameras, probably just go right to the unit. Also recommends a breakout box. Here's why. If we look at the connector, it looks like just a 4-pin round connector. Looks very similar to maybe an S-video connector if you're familiar with video. And it has our different data points here. So if camera supply voltage, we have positive video and negative video, or negative video and positive video, should I say. And then 5, note how it says not an actual pin. That is our coaxial shielding signal for the mirror. So as I said, like a braided metal, we don't want to pierce that. So we don't want to, so that's why we want to use a breakout box. We can put something in between the connector and then piggyback off of that. And also we see on pin 3, camera LIN bus for the mirror. All right, so LIN bus is how we're controlling the network signals going back and forth. So that's what we're going to test. So we'll hit the back button on the top, and we could do a DC voltage test. That'll have us test for battery voltage. We're going to go into a signature test. So in this case, in the signature test, they want us to check that LIN bus, as I said. So LIN is local interconnect network. It is a relatively slow speed data bus. It's really used for control signals. And black to known good ground again. If we go all the way down to the bottom, we also see a known good typical LIN bus signal. So we'll see it as just a square wave, right? So we have a bottom and a top, and they're squared off on the bottom and the top. If we hit view meter, we would pull up our meter and we'd be able to see that information on the screen. Now, I can't simulate a LIN bus with my equipment, but I do have a saved known good LIN bus pattern. So I'll pull that up and let's take a look. So if we were to hook up to a vehicle and test the LIN bus, we'd see something like this. Every time these square waves go by, that is transmitting a piece of data back and forth, signals between 2 modules, right? So you see it gets a little noisy there. It's actually when the vehicle turned on. But with the vehicle off, we could also see it as well here at the beginning. So let me pull up the beginning and see what we can get for a pattern here and talk about what we're looking at. All right, that's fairly, There we go. That one looks pretty good. Okay. So let's turn on our cursors and take a look at what we have going on. So here's our bottom, round about there. Here's the top, round about there. We're close. And what we want to see on a LIN bus system is the high and the low are dictated by conditions in the vehicle. So the high side will be whatever alternator voltage is, battery voltage is. Right, so in this case, on the high side, I see 13.21. Then the low side will be dictated by whatever that high side is. There needs to be a 12-volt difference between the high and the low. So if I have higher than 12 volts at the top, then I'll have higher than 0 volts at the bottom. So in this case, I have 0.82 volts, 12.38 volts. That's close, really close. We see that's not exactly a straight line either. So this is as close as we can get. So roughly 12 volts. We want to see a 12-volt voltage differential from top to bottom on a LIN bus. We want to make sure that the top and bottom are fairly square. We don't want to see any noise. We don't want to see any dropouts or glitches. If we had maybe it's a 5-volt signal here instead of a 12-volt signal, that would be something wrong in the wiring, right? We would have we don't see that 12-volt difference. That's mainly what you want to look for, is a 12-volt differential. That's LIN bus. Now let's take a look at our radar. So go ahead and pull that Land Rover up and look at the radar. So go to guided component test again, hit OK. Driver aids and ADAS. And we're looking at the blind spot monitoring module, right? So let's look at that. Component information. So functions to warn the driver of vehicles in their blind spot. Each module is connected to the medium speed CAN network and each other with a private CAN network. The radar sensors operate at 24 gigahertz and are integrated with the modules. Location. So the components are located attached to the body behind the bumper cover, one on each corner. Now we saw that in the shop key information, right? Now the 8-pin connector at each blind spot module is the best place to test it. So you may need to remove the bumper to get there. We have our connector view up here. It tells us what each wire does. We have 2 CAN buses there, ground and location identification. So either power or ground. We go down to tech notes. It tells us more about that. So the 2 blind spot monitoring modules identify their position on the vehicle via pin 3. The left module wiring has battery voltage at pin 3, and the right module wiring has chassis ground at pin 3. So depending on what is on pin 3, we'll tell the vehicle I'm left and I'm right. Once we have that information, we can hit the back button. And the only test we can do in this case is a signature test. We're actually going to check the network. We're going to check the CAN bus on this vehicle. And actually, I got to hook that up. So let me plug this in while we're talking here. So we look at the top. It tells us how to hook it up. We have the yellow to high-speed CAN high. And then on the other one, it says yellow to high-speed CAN low. So in this case, they want us to check one signal at a time. So we can do that. We'll hit view meter. Once again, sets the voltage range where it needs to be, sets the time base where it needs to be. And now I see my signal. This is actually my CAN low signal is what we're seeing here because it's going down to about 1.25 volts. So we pull that down a bit. We can move this around. Make it a little easier to see. There we go. So this would be our CAN low side, so right there. Now, ideally, when you're testing CAN, you really want to look at 2 channels at once. You want to be able to see the high side and the low side, see if there's any differences, any anomalies, because they should be mirroring each other. Now, in guided component tests, yes, it does set everything up for you, but did you know we can actually add additional channels and change the settings inside there as well, just as we could inside the lab scope. So it gives us a nice starting point, but then we can tweak and change and modify to our heart's content. So let me show you how we would do that. So we go on the top where it says meter. That'll just make it easier to see when we go to our settings screen. I go down to the bottom here, pulls up my measurements, and then it pulls up my settings. So if I wanted to add an additional channel, you see I'm on a 4-channel tool, so I have 4 eyeballs here. If you're on a 2-channel tool, you have 2. If I want to turn on channel 2, I'll simply click that, and then my channel 2 is on. And I am connected to the CAN bus on this too. And you might be saying, well, I just see a flat line there. What's going on? Why don't I see a signal? Reason being is, if we look at the scale from my channel 2, that is set to 400 volts. So that means at the bottom of this window to the top of this window, that is 400 volts of measurement. And this is only a 1.25 volts, volt and a half worth of signal. So we're not really seeing any motion down there because of 400 volts. So let's change that. So we go over where it says scale and click on that, and we can set that down to 5 volts, just like the other channel. There we go. Hit back. Now they're both on the screen, one next to the other. That's a good look for us. And you might be saying, well, I thought that it automatically set the voltage for you. Well, it does for the 1 channel. Anything else, if we add additional channels, it's just going to be wherever the preset was saved at the time. So in this case, we needed to change that, and that's okay. But it can be done. Now we see both channels here. We see CAN high and CAN low. Now, to me, 5 milliseconds, that's a pretty high level view, right? I can see, do I have any quick shorts to ground, any quick shorts to power, that sort of thing. But I want to get a little bit more in depth. I want to get a little closer to this signal so I can see just more of that data packet on the screen. So in order to do that, we'll change our time base. So right now we're looking at 5 milliseconds going by. If I click on the time, I'm going to bring that down to 200 milliseconds. So now I can see a lot closer of a view of those data packets, right? So I'm going to stop this recording so we can take a look. Okay, so here's my data packets. Let me bring it back here a little bit. There we go. That's good. So we have a flat line here, you notice, and then we have these pulses. These pulses are the individual bits and bytes, the ones and zeros, the data points going back and forth between the modules on a vehicle. CAN bus communication is used on many vehicles nowadays. Most of your 2-wire networks are going to be very similar, even if it's like, say, FlexRay. That'll still be a very similar look to the signal as well. But the nice thing about CAN is it's a standard, right? So for testing CAN, we know what to look for. So let me pull up my measurements and pull up my cursors and see what we're looking at. Now, remember, we're in a testing environment, so it's not 100% exactly what you'd see on a car, but it's really close. So here we have the flat line. When we have this flat line, both channels should be at pretty much 2.5 volts. We should see 2.5 volts on both lines. And that's what we consider an idle state. So that's just a neutral, not transmitting anything, just sitting there with the key on, should see 2.5 volts. When it transmits data, these data bits and bytes right here, all these different data points, the high side will go up from that 2.5 volts, up by about a volt, volt and a quarter. And then the low side will go down from there about a volt, volt and a quarter. In this case, we see it goes down 1.26, goes up 1.235. That's very close to that volt and a quarter or so. They should match. They should mirror each other on both sides. Now, why do they need to mirror each other? Because we're watching a round trip. One side goes out, high side goes out, low side is receive. So transmit on the top, receive on the bottom. It can still communicate even if we are missing one of these sides. It just won't communicate as fast, and you'll get errors. We want to see the voltages in this range. If we saw 0 volts, that's short to ground, so that'd be out of range. That'd be way down the bottom. If we saw short to 5 volts, that's up right at the very top of the screen. That's outside the range, right? So that'd indicate a short to 5 volts. And then 12 volts would be off the screen, right? So any of those conditions are bad when it comes to CAN. Also with CAN, you want to make sure there's no noise, so you can definitely get RF noise in there. We want to make sure the packets look good and flat on the top, flat on the bottom. I mean, this is, like I said, testing conditions as close as we can get. If you ever connect to a real live car with a known good system, should be nice and flat, as long as you don't have any interference there. There is one time or one occasion where you will see a larger square, and it'll be at the end, at the tail end of one of these packs, right? So it's going to transmit data, and then the very last little bit here would be higher. Maybe it does go down close to 0 volts. Maybe it does go up close to 5 volts. Some systems are designed that way, where they transmit what they call an ACK bit or an acknowledgement bit. So that basically tells the computer, hey, here's the end of that data packet. I'm done. Stop, period. Here's the end. And then we'll transmit another one. Right. So here it is. Here's the end, and make sure that's good. And then we move on. So you may see one data packet at the end that's much taller than the rest. And don't be worried about that. That is normal on some systems. In this case, it does not have that bit. So it just, they're all the same. The main keys we want to take away from testing CAN bus, and this is a super fast, super high level CAN bus course, because we actually have other course material where we talk about this a little more in depth. So you want to have that 2.5 volts on both channels. Goes up by about a volt, volt and a quarter, down by about a volt, volt and a quarter. Should be in this range. Should roughly look in this way. You know, where you have flat tops, flat bottoms, fairly square corners. This would be a known good pattern in this example. All right. So in that case, that's how we would test the CAN bus on the radar system on this Land Rover. All right. So that is our material for the evening. Now let's talk about next week. So thank you for joining us this week. If you have any more questions, I'll be getting to the chat on YouTube in a minute. Put them on the Q&A if you're on Zoom joining us. And make sure you tune in next week if you want to learn more about that guided component testing, because I know we only talked about it for a very short amount of time. So we're going to go a little bit deeper into component testing and why we would want to use it, and some sample applications, look at some sample signals there. And definitely would want to use it versus scan data for sure, because the difference is really in the details, as it says there. So same time, same place as we dialed in for this. You can catch it next week. Also, if you can watch it on YouTube as well, we're streaming session 2 on Tuesdays for the next few weeks. And also, if you're on YouTube, be we'd be very welcome if you would like the video, subscribe, and make sure you turn on the notification bell so you'll know the next time that we're live streaming. You can make sure you see all our videos when we put it out. So it is Snap-on Diagnostics is the username on YouTube there. All right, so Snap-on Diagnostics. So with that, also, I would like to mention before we get to the questions, we have also another new training modules that we just put up. These are live trainings as well. My friend Al McCaskey does these, and they're on Mondays. They're for Apollo D9, our new Apollo D9. Wednesdays they're for Zeus, and then Thursdays they're for Triton D8. So this is really a buttonology setup type course. So if you've just purchased a tool, that'd be a good place to go. Also, it talks through setting up Wi-Fi. So if you're having difficulty with that, we can help you with that. Also, it walks through setting up your free Altus Cloud account. So if you haven't gotten around to that, you may have had your tool for 2-3 years and still have not done that. We walk you through that as well. It's very simple to do. We'll walk you right through it live on screen. You'll be able to see the screens as we go. And you can register for those classes at the same place you can register for these classes. So that is snapon.com/NOT. It's very simple to remember. Snapon.com/NOT, and NOT stands for National Online Training. So I'm going to leave that up there, and we will go to questions. Let me look at the Q&A on Zoom first. Looks like we have many people helping us on chat, which is great. Michael, let's see. So Chris says, thank you, Chris. Michael says, what does LINBUS stand for again? So that's local interconnect network. Yeah, that's what that stands for. GM calls it something different, so I had those two terms confused in my brain there for a second. So yeah, local interconnect network. Let's see, got you there. And then Paul, thank you very much for coming. It's good to see you, Paul. It's been a while. I appreciate it. I saw you registered today, so very much thanks for coming. All right, so that takes care of that. And then let's go over to our chat. Looks like chat got taken care of. What is wrong with your audio? You sound like a robot. That could very much be Zoom transmitting to YouTube. I hope the audio problem would get corrected by now. I hope so. And then you also asked, can you recalibrate it without the targets? So Kyle asked, can you recalibrate ADAS without the targets? Depends on the system, depends on how it's set up. On some systems, we have what we call a dynamic recalibration. We touched on it last time, so if you want to check out that intro to ADAS video, we have it in there as well. But example of, say, I know we worked on a Cadillac, right? Cadillac SRX, the camera system. On that, they call that a dynamic test, and you just simply drive down the street under set conditions, and it will recalibrate itself based on the conditions there. Okay, let's see. Oh, and actually Todd already answered that as well. So good job there. And then let's see. Sergio says, an important note is that Mercedes vehicles need to have the adaptive cruise control recalibrated after alignments are performed. Targets are not required. You must follow the vehicle at specific feeds. Perfect. So Sergio, that is another example of that dynamic recalibration. And yes, absolutely. Anytime you align pretty much any vehicle with ADAS on it now, you do need to perform at least some sort of a calibration on that vehicle as well. So excellent comment there, Sergio. Looks like we got everybody answered. Oh, there we go. Great info. Can't believe it's free. Thank you very much. Yeah, I can't believe it's free either. So it's I'm glad to be able to provide this for you. I'm glad Snap-on's able to provide this for you all. And hopefully we'll see you back next week, right? And hopefully you tell your friends so we can have more folks go through this training. It's always good to have more training in your life. Can't go wrong with more training. All right, with that, I think we're good. Todd, what do you think? I think we're good there too. Okay, with that then, thank everyone for attending, and hopefully we'll see you next time. Hopefully we'll see you on another one of these training sessions, and hopefully enjoy the rest of your week. Take care and have a good evening.